Hi all, welcome to another session from Naiva Research. I'm Srijit here. So in the last session, we have started the introduction about diffusion coefficient and how we can perform the calculations using reactive force field. So in this session, I'm going to continue with the typical example that how we can build a system. So in this case study, we are focusing on how to compute the diffusion coefficients of lithium ions in a lithium sulfur cathode by means of molecular dynamic simulations with the reactive force field engine. So the systems and workflows presented here are originally described in a publication uh, named Reactive Force Field Molecular Dynamic Simulations on Lithiated Sulfur Cathode Materials, which was published in 2015. So in the later videos, I will show you that what are the different inputs I have taken for this typical calculation. So in this typical tutorial case study, we are focusing on how we can import a zip file and how we can manipulate the structure and equilibrating the system, creating an amorphous structure using simulated annealing, and how we can calculate the diffusion coefficient from the MV trajectories. So first part is that we need to perform a geometry optimization. So before that, I would like to give you a brief idea that why we perform this optimization. In order to relax the geometry with a lattice relaxation, the goal is to optimize both the atomic positions and the unit cell parameters so that the total stress and forces are minimized. So this is essential for periodic systems such as crystals, surfaces, and battery materials. So where the equilibrium lattice constants may differ from the initial guess. So in Amsterdam Modelling Suite, this is handled through geometry optimization with variable cell, allowing the system to reach its true ground state structure under zero external pressure. So in practice, generally within AMS, we use ADF and DFTV engines. So lattice relaxation is enabled by selecting a cell optimization or various lattice options in geometry optimization task. The optimizer simultaneously minimizes the atomic forces and the stress tensor by adjusting the lattice vectors. We can control the optimization algorithm, which converges the thresholds for force and stress. And also after convergence, the optimized structure provides relaxed lattice constants, cell volume, and internal coordinates, which are crucial for reliable property calculations such as elastic constant, diffusion coefficient, electronic structures, and even bonds. So in this specific case study, I have already imported that lithium sulfide structure, so which contains almost 128 atoms. So here I'm going to perform the optimization, where I have already selected the lithium sulfide force field from the force field library. So here in geometry optimization, I'm just checking off the lattice optimization tab, and I'm just performing the optimization calculation. I'm just saving it. Underscore lat opt. So it is a file name lattice optimization. And I'm saving it. So this will be the primary step before proceeding for the further calculations. So let me run the calculation. It won't take that much time because it will be a simple step. So we can check the progress of the calculation. So you can see the termination is happened normally, and it won't take that much time. So let me check. Click on S for continuing the calculation, and now we will go to AMS movie, and we will check the output, and you can see that how that frame has been created, and then we will go to graph and then cell volume. So let me go to cell volume, and then when we click on this, you can see the frame number and the energy, the gradient max, and the optimization status of that specific calculation. So by this, we can perform the optimization of the specific battery material or that lithium sulfide material. And you can see that how much time it has taken to perform the calculation and how much is the observed cell volume and energy parameters. So with this, I'm just finishing the session, and in the next session, we will be focusing on the further dynamics and how we can observe the diffusion coefficient calculations. Thank you.